Yeah, so today's lesson, we're going to be looking at light and optics. And in particular, when we speak of optics, we're talking about what we see, right? What we see. And we're going to expand a little about what we see in mirrors, and we're going to talk a lot about the reflection of light, the reflection of light, right? The optics of it. In other words, what we see. And in particular, when it comes to mirrors, we're going to talk about what we call concave mirrors, And of course, we'll talk a little about their uses, right? And then we'll talk about convex mirrors. And also, of course, for both of them, we'll talk about the optics, what we're basically seeing them, right? And their uses, right? So that's what we're going to cover in this lesson, right? So let's start with light, right? Um, Light is, even though it's all around us, it's one of the least understood things in nature, right? And there are two schools of thought, you call it. One of the schools of thought says that light is a electromagnetic wave, right? It's a EM wave, right? Which involves an interplay of electric and magnetic fields and so, right? And they have their own evidences of that, right? They say that, well, all waves go through what we call reflection, refraction, and there's something called diffraction as well, diffraction, right? We're not going to deal with these, especially diffraction. We're going to talk a little about reflection, refraction, but not diffraction, right? Yeah. So they point to light behaving like a wave because it undergoes these here. And then there's another school of thought that says that light behaves like a particle, right? And there are certain things they point to, right? That they say that, you know what, because of these things, um, they say that, look, light is a particle, right? For example, there's something called the photoelectric effect. Photoelectric electric effect, right? Um, that actually models light as a particle, and it actually tells you that, well, light is like little packets of energy, right? And the energy, I think there's a formula for it too, like that, right? Yes. Um, where you actually measure the um the amount of energy, right? Um, that the light carry by that formula. Anyway, we don't have to know this. I'm just saying that they point to this here as as one of the evidences, right? I think it's the guy Albert Einstein talked about it, right? That light actually behaves like a particle. And they say that, well, well, as a matter of fact, our solar panels on the roof um kind of lends evidence to that the little bit of energy in each packet of light, of energy that is carried by the light, hits the electrons and move them around in the material that makes up the solar panel, and that's how we get current, right? We get electricity from a solar panel, right? So, but we're not going to wrangle about these arguments about light, right? We're going to go to especially if you're interested in how light is used, right? How light is used in everyday life, in the sciences, and for you and me, especially in the light of this course, talk about our own well-being and safety, right? It's very, very important that we understand. Well, we're talking about here about mirrors and their uses, you know. But before we can get to that, really, we have to understand mirrors a little, right? And as I said, I think I left out a category of mirrors that we have to deal with before we talk about concave and convex mirror. Plane mirrors, plane mirrors, right? Plane mirrors. We, that's the main one, right? First and main one. Good. So let's talk about them. Let's talk about them. So before we go there, right? How are we going to model, light? How are we going to, treat it before we can really understand its behavior? Let me just bring this little diagram from our notes uh, for the benefit of our class. Okay, so yeah, look at this diagram here, and we're thinking of this pulsating sphere here as though it's pulsing light, right? And when the light goes out from it, what we see is that the rays each, and that's what I'm talking about, modeling light, right? So one of the ways we model light is to think of it that, the light consists of rays, right? And the rays will actually tell you, well, all right, the light is traveling away from the source and going, and you notice they're using straight lines, right? So for now, we're going to think of light as rays that are traveling away from the source and they're traveling in straight lines. Now, if we were to go away very far away from this source here, the angle at which the rays are going to travel is as though they're parallel, right? So this curve wavefront as we move away very far from it, right? Like look out where we are from the sun, very far. So these angles will not make any sense to us, It's as though light is coming, um, you know, uh, on a plane wavefront rather than on a curved wavefront, right? Because when we think of the source, let's say this is the sun, right? Let me go back here. Yeah, if this is the sun, right? By the time light reaches us, it's as though it's coming to us as parallel rays, right? So in our entire discussion about light and how it forms images in front and behind a mirror, and so we're going to treat light as a set of rays, right? And sometimes we shrink down the whole thing to just being a single ray, right? Or a few rays, just for us to understand, well, how images and so are formed, right? So we'll treat them, you'll see us sometimes taking a ray, one ray, two ray, three rays. And so just to help us to see how images and so are formed, right? So that's how we're going to treat light. In other words, we're trying to model light, right? As I said, we hardly understand the thing, so we try to model it. And the model we're using is going to help us to understand its behavior for the most part, right? So we're going to treat them as rays that are traveling in straight lines, right? Good. So now that we get that out of the way, that we're going to treat light as rays of light that travel in straight line. As a matter of fact, if you were to treat these little planes here that you see, right? If you were to, let's say this particular ray here, that as though it's a hole here and here. If you were to move this out of the way a little, right? If there was a third one, let's say we had a third one here somewhere, right? A third one here, and the hole is here. If you were to take this one in the middle and move it to that side, what's going to happen? This ray will not pass through, right? Because it's going to block the light. So it's justified that we're treating light rays as traveling in straight lines, right? Of course, there are those who will argue with that and tell you that light do curve around when it passes certain object and so on. We're not going to get into those debates, right? Um, Sometimes you got to be careful with your audience, when people are too learned, um, they argue everything. Good. So what we want to do is we want to start with how light is reflected, right? How light is reflected. And again, let me just take a moment and bring across a diagram that will help us to understand how light is reflected, right? Good. So now that we have a little diagram here with um, a statement of the law of reflection, right? I'm not going to get into, these law. The scientists like to run anything they find out, they call it a law, right? We don't use that word so much in physics or any of the sciences anymore, right? I think they favor now using the word principle more. But let's take it as it is, right? It's the law of reflection. And here in words, it's saying that, okay, they talk about an incident ray, they talk about a reflected ray, they talk about something called a normal, and it says that they're all in the same plane, and the angle of reflection equals to the angle of incidence. So they're trying to show all of this here in the diagram, right? So what you're seeing, all right, so the incident ray means that's the ray. So we're modeling a beam of light. So look, we're not taking the whole beam. Take just one ray out of it, and we want to explain how this ray will behave when it bounces off a certain surface, right? And so when it hits here, so this is your mirror, right? And in this case, we're saying that okay, we're dealing with a a flat mirror. Later on, we're gonna get into what you call concave and convex mirrors and so, right? And the law holds, right? It behaves the same way there, right? It's just when it bounces off, how it's going to look and so on. And that's going to be a little different. So the incident ray is a ray that comes down here and hit the mirror. And it bounces back in such a way that if you were to draw a line that makes a right angle, it makes a right angle with the mirror, right? Makes a right angle with the mirror, right? This is what we call a normal. It's a line that is perpendicular to the mirror. So if the mirror, if you were to watch it sideways, um, the normal line looks like that, and it makes a 90-degree, right? I know I don't have a perfectly straight line, right? Yeah. Um, so yes. So if you were to take the incident ray along with the normal and the reflected ray along with the normal, the angle of incidence is equal to the angle of reflection, right? And you notice they say they're on the same plane. So if you were to take the plane, right? Or take a plane is a two-dimensional space. If you were to take a plane passing through there and go up here like a thin sheet of paper then, right? This line lies on the paper. This normal lies on the paper, right? And this reflected ray lies on the paper as well. All three of them lie in one plane. That is what it means, right? All right, my grandchildren are making too much noise. I need to. Yeah, this is the just an illustration of the law of reflection, right? Um, so here is a solution, a chart demonstrating the reflection of light on a plane mirror. Right? So, yeah, short, but I think it illustrates the point. Maybe we can play it a second time. Right? So you see um, the incident ray, all right, it's at 30 degrees. You see where it's reflected, right? Same thing with the 45, same thing with the 60, and they all lie in the same plane in that it's all happening on this surface here, right? Yeah. Well, not every time you'll have a situation where you have a nice flat surface and so, right? And therefore, you might very well have a situation where, as the notes brings out, you have a different type of reflection where, let me see if I can cut this. Yeah, yeah. So look here. So you have a situation where, right, you have specular reflection, so it's nice and straight, So you can see the law of reflection being demonstrated very easily. But here you might want to question what's happening here, really, right? Because of the unevenness um, of the reflecting surface, the reflection is not so uniform, right? So they call it diffuse reflection. But the law holds. If you were to manage to, let's say we isolate this point here, right? And draw a flat surface here, and we were to draw a normal, right? You'll find that indeed the angle there is equal to the angle here, right? Yeah, so it does hold. It's just that um, it looks fuzzy and the rays are going to be bouncing around all over the place and so, right? And you have both of these situations you see in real life all the time, right? And if you were to, study light and colors and all these things to a high extent, you'll get to see how people can use diffuse reflection and other behaviors of light to create certain effects and so, right? Those people who are into fashion and those who are into studying painting and all of that, they could make use of these things to really, create certain effects and so. But we're not going to get into all of that. We're doing a basic course where we're just trying to understand, um, you know, how light behaves when it goes and it's reflected on a mirror, right? And as we said, we're going to start with plane mirrors. Plane mirrors. All right, let's start here. Let me go and grab um, a little image for us. Good. So now that we have the image here, we want to note a few things about um, images formed in plane mirrors, right? So well, you can figure out that that little blue surface you're seeing there, right? It's basically the mirror, and there's a man standing in front, right? So there are certain properties of the image that is formed in the mirror, and the first one is that okay, just like the man is upright, you see the image in the mirror there. What he's looking at is also upright, right? So the image is upright, image upright, right? Just like the man standing upright. Um, Secondly, we see that the image is the same size as the um, I'll call it the object, right? As the object, right? The object is the man. Thirdly, we're seeing that the image is located um, the same distance, the same distance behind the mirror as the object is in front of the mirror, right? And 4, the image is laterally inverted. Good. So, all right, let's take them one at a time. All right. So we said that the image is upright. No dispute about that. The man is standing up, right? And the image looks like just like the way he's standing. Nothing controversial about that. Here's the next one. The image is the same size as the object. Now, because this mirror is what we call a full-size mirror, I think there's no controversy there, right? There's no controversy there. It seems as though the image is exactly the same size. And there is some controversy here, and I'm not going to raise it now. I'm going to wait a little, right? So you have a mirror, and the mirror is as big as the man or even bigger than the man. And we have no controversy. The image is the same size as the arm. I don't know if you have a big mirror at home, and if you have ever gone right up to it, maybe you put your nose to your own nose in the mirror, and you see the exact same size, right? Maybe you have done that, right? I've been silly enough to do that, right? I go right up to the mirror, right? And put my nose and let my nose touch the nose in the mirror. Right? Call me foolish, but yeah. We're going to come to a situation where you're going to dispute this in just a moment, right? And then it says the image is located the same distance behind the mirror as the object is. And again, this is a little, it's a little, because the mirror is just a thin piece of glass, right? But it appears that, okay, if you were to put a measuring tape from the mirror to the man's foot and you put 1 meter there, right? And you watch in the mirror, you will also see 1 meter being reflected there too, right? And I think that's what we're talking about. It's perceived that way, right? And we'll see how that will help us even with the image size as well. If you were to take a measuring tape, and you were to hang it on yourself, maybe from your neck here to the ground, and okay, that's 1 meter, right? I'm just saying. You will see in the image here from the neck to the ground also for the man, you're going to see that same measuring tape as 1 meter, right? And it seemed to be going well for a mirror that is as big as you are or even bigger, right? We can come to, some controversies in a moment. And then this one here it takes a little bit of explaining too. That the image is laterally inverted. In other words, this man here, he has his right hand up, right? But if this was a person in this image here, that's his left hand, right? So it kind of invert you then. It inverts your right hand becomes your left hand becomes your right hand, your right eye becomes your left eye, and so on and so on and so on, right? So you have to be conscious of that, right? You have to be conscious of that. And there is something, so keep these 4 in mind, right? Keep these 4 in mind. We'll come back to 2, 3, and 4 when we don't have a mirror your size, because not everybody can very well have that, right? And sometimes you have situations where your mirror is not life size, right? And how are we to interpret what's going on in the mirror? And so we can come to that. Oh yeah, I was going to point to a case where lateral inversion is made use of, right? And I remember, and maybe you too, when you watch the ambulance, right? When you watch the ambulance, let me just yeah, when you watch the ambulance, you want to know why is it that they write the word ambulance this way? right? And the reason why is that if you are in front driving and you take this word ambulance, and when you watch in your well, oh, by the way, that's one of the use cases of plane mirrors, right? You know this rear view mirror here? Where is it? Yeah, this rear view mirror here, or yeah, this rear view mirror here. Um, in lots of cases, this is a plane mirror as well, right? There are times when you also use a convex mirror here, but um, this could also be a plane mirror, right? A plane mirror, right? I noticed the internet, and sometimes you can examine the mirror in your own car to see if it's a plane one or it's slightly convex, right? But we can come to that a little later. So yeah, this is a, let's say it's a plane mirror. What would happen is that this word is going to be inverted, and you're going to see the word ambulance spelled the right way, right? If you are driving in front. Oh, not this mirror. Let's say you are in front of this guy driving. You're going to see the word ambulance laterally inverted. So the A comes here, ambulance. You're going to see this. You're going to see ambulance. Um, oh, I left out M, no? Yeah, ambulance. Yeah, you're going to see the word properly, right? And you're going to know that, you know what, somebody has had an accident or has fallen sick and they're racing to the hospital. Get out of the way, right? So that's a clever use of this whole idea of lateral inversion in plane mirrors, right? Interesting. Good. Good. So just to give you an idea of how we perceive the image um, in a plane mirror, this is what we call a ray diagram, right? So this is basically what happens, right? So here's the object, right? The light from the object, light bounces off, right? And we're treating it again as a ray traveling in straight line, hits there, and then it goes up there. But when you watch the eye kind of perceive, because this might not be in the what you call your periphery vision, or your, let me put it, your line of sight. It's not in your line of sight. Sometimes it's not even in your what you call periphery. You're not, maybe it's a little blurry, you're not seeing it. But guess what? Because of the way the eye is, right? The angle at which it is, it's seeing this as, look where, it's as though it's coming from the back here, and that's what you see here, right? That's what you're seeing here. So the image or this object here is seen to be inside of the mirror, right? It's not that this image is actually um, this far back inside of the mirror. But remember, the mirror is it's a very thin piece of glass, but it appears to the eye as though it's as far back from the mirror, right, as far as the object is from it, right? That's how it perceives it, right? And we have to kind of wrap our heads around it, right? We have to wrap our heads around how the eye sees things in a mirror, right? So in this case, it looks like it's a full-size mirror. So yes, the object is the same size, it's upright, it's same distance away as well. But let's go to a situation where you don't have a full-size mirror. So what happens? What happens? Can you still see the full size of things, right? The full size of things. Even though you don't have a full mirror, what can you do to ensure you see the full size of things, right? When you don't have a full size mirror. That's important in real life, because you can't walk around, or in your car, and so you can't have full size mirrors. That's not going to be practical and convenient, and so let's look at a situation when we have, let's say, a half size mirror, right? Could we see our whole selves in a mirror that is half our size or even quarter of our size, right? That's the question. Well, let's see. Let's see that. Give me a second to grab an image. Okay, yeah. Now that we have the our image, right? So here it is. We have a woman standing in front of, well, it's a full size mirror. It's a full size mirror. And the question we're tackling is whether you need a full size mirror to see your whole self, right? You're questioning yourself, right? So what we actually can see here from the ray diagram is that the woman's foot is in a position that when we were to check here, when it touches the mirror and goes towards our eyes, right? This angle, the two angles are the same. It obeys the laws of reflection. And therefore, we basically don't need, if I'm to take this part, we don't need this part of the mirror. We don't need this part of the mirror, right? So this woman can actually see her entire self in just half the mirror. You see? So once the person puts herself at a certain distance where this angle, right, that the foot makes with the mirror and the eye here is the same, this angle equal to that angle, right? Well, they're going to see their whole self, right? And basically you're seeing that, well, that's what they call a half size mirror, right? A half size mirror. In other words, you can actually have a half size mirror and still see yourself, your entire self in that half size mirror, right? And a little bit of geometry will actually will have to tell you based on, you know, the woman's height and so on. I don't want to get into the mathematics of it, right? Based on the woman's height and so, there's a certain distance that she has to be away from the half size mirror so that this angle here, right, is such that it catches her eye, right? It bounces off the mirror and catches her eye, right? So she has to adjust. And maybe you've done that before. You have a mirror at home, it's not so big. What do? You simply move away from it to some distance, right? So it's on the wall and maybe you're seeing from your waist up. You say, no, man, I want to see how my foot and how me, how me look with my foot and so. And you move away from your mirror, right? So the idea is that you move away to the point where this incident ray from your foot, right, goes straight to your eyes. This angle here has to be such that it allows that to happen. And in that way, you could actually have a half. You could even have a quarter mirror. You could have a mirror that is a quarter your size and still see your entire size. All you got to do is move away from it, right? Now that brings up the controversy. Now remember we talked about, and maybe we can deal with that as we're here. Remember we talked about the mirror, what did you say? The image is the same size as the object. We said that, and the distance behind the mirror, where the image is behind the mirror, is the same as the distance in front of the mirror. Remember we talked about that? I think there were 3 conditions we said. The image has to be the same size. Let me see if I can go back. Oh my. Let me go back a little. 1 second. Yeah, we said the image is the same size as the object. The image is located the same distance behind the mirror as the object is, right? In front. Okay, these two. The lateral inversion is not a question. The uprightness of the image is not. These two are the ones that were controversial. So let's say, all right, give me a second. Let me see if I can get back. Yeah, get back this here. Good. So you have a nice image here. So here you are in your car. You know that your rear view mirror is a very small mirror. You probably have what maybe 3-4 inches this way by about 6 to 8 inches this way, very small. And here you have a car behind. Now you know the car in this mirror is just going to be a couple of inches, right? By a couple of inches, very, very small, right? How is it we're saying that the image is the same size, right? So what we're really talking about here is in terms of proportion. When you look at the other, okay, look at all the other cars here, right? And so the image of the car is in proportion to these other cars. And if you were to, let's say you were to put a measuring tape on the real car, and from here, let me go down here, from here to here is about, let's say, 1 meter, right? 1 meter. Well, the car will appear to be 1 meter as well, right? It's going to read 1 meter there, right? Similarly, if you have some kind of measurement on the road here, and the car it's saying that the car is 10 meters behind you, you're going to see 10 meters here on the ground as well, right? So when they say it's the same size, they're talking about in proportion with everything else, right? A good illustration, and I was looking for a good illustration to tell you. It's like, okay, you see a building. A building might be 50, 60, let me say 50 feet high. But you're far from it. You're far from it. It looks small, right? To your eyes, it looks small, but it's still 50 meters high, right? So it's because of what we call perception, where you are with reference to the building. It seems smaller to your eyes. You perceive it to be smaller, but it's still 50 meters high, right? Same thing with this car. Because of the mirror and the ray diagram and so would make it look like it's small here, but it's actually the car is the same size as the car at the back when you look at relative to other things, right? These cars, all of them are very well, whatever height they have, compared to this car, it's the same in the real world as you see on the mirror, right? Of course, we're assuming that this is a plane mirror, right? It's a plane mirror. As I said, some cars would have a plane mirror there. Others might not have a plane mirror, right? They might very well use a mirror that would make the car seem a little closer. And the whole idea is that to get you to kind of think that, the car is closer, and therefore you were to maintain your distance by going forward or not taking a right or left turn, So they do that. But in this case, let's say it's a plane mirror. Right, that's a use case of plane mirrors. You see them in these rear view mirrors. The side mirror in the car too, the side on these little ears like this here. Sometimes they use plane mirrors there too, right? Not always, but they do use it. It depends on your car, and so you can always check that out to see, right, whether it's a plane mirror or it's a convex mirror that you're using, right? But they do use plane mirrors in these scenarios here, right? That was just to illustrate that same thing. So when it comes to the size, they say the size is the same size and the same distance behind the mirror, the image appears. But what we really mean is not that the car is 1 meter. That image can be 1 meter because this mirror is just a couple of inches, right? What do you mean? In proportion to everything around it, right? When you look at a car, you don't think that, this car is probably 2 inches or 4 inches or what on the mirror. No, you think of it as the size of the car. The reason why is that the size of the car in proportion to everything around it that you see in the mirror is the same. That hasn't changed, right? It's because of your distance away. That's how it appears, right? I don't know if I hope that explanation is sufficient for you to understand, right? Because I myself asked that question, man, how is it? This car is not the size of the car behind me, right? Because it's showing in a little mirror. But what we mean is the size of the carrier in proportion to everything else around it. It is the same size, right? And it does appear to be the same distance you are, the carrier is behind you, right? It appears in the mirror there, that same distance behind, right? So keep that little thing in mind. And then you can actually see the inversion in terms of the carrier number, right? If the carrier number is 1, 2, 3, 4, you're not going to see 1, 2, 3, 4. The number is going to be inverted, right? Yeah. So I hope that kind of takes care of that seeming controversy like that we have about mirror size and whether the image is the same size or the same distance away, right? Good. So our next move now is we want to look at what we call spherical mirrors, right? And those spherical mirrors we want to talk about is concave mirrors, and then we'll deal with convex mirrors, right? We'll take them one at a time, right? We'll start, of course, with we can start with concave mirrors. Concave mirrors. Good. So here we have some images. And here we're dealing here with concave mirrors, right? Notice that this is the mirror surface, right? And the silvering is like at the back here, right? That's why you call it a concave mirror. So it's bent inwards, right? It's bent inwards. So those mirrors shaped like that are concave mirrors. Good. Now, in order to help us to understand how the image, how we can plot the image of an object in a concave mirror, these are what you call ray diagrams you're looking at here. I know I kind of throw them in your face, but yeah. So notice how you go about doing it, right? The first thing you do, you take, okay, this is the object here, right? And take a ray that is parallel to, I should mention what these letters and so mean, right? So this is your mirror, right? The C refers to the center of curvature. And the distance from C to the mirror is what we call the radius of curvature. And draw a complete circle. If you were to draw a complete circle with it, the C here will be the center of that circle. They call it the radius of curvature, right? And F is what we call the focus, right? Focus. What that means is if you were to direct some parallel rays to this curve here, they're going to bounce back and pass through the focus there, right? It's kind of focus all the light in one place. Concave mirrors are not very good at that, right? There's another type called parabolic mirrors, right? There's a type called parabolic mirrors that is very, very useful in generating electricity and so. I'll probably put up a picture in a moment. It's in our notes there, right? Yes. So this is our center, right? Center of curvature, right? And this is our focus, right? And there is a relationship, right? There is a relationship between F and this distance, which we call this here the radius of curvature, right? This is the center of curvature. This is the radius of curvature. And you can see that F, the distance F, right? This distance here, F. right, is actually half of R, right? That's not hard to see. That's not hard to see. But let's talk about how we get the image that is formed by this object when it bounces off the concave mirror, right? So the first thing we do is that we try to draw a ray that is parallel to this black line here, which we call the principal axis. It's a line that passes through the radius of the center of curvature and the focus, right? So it's called the principal axis. So draw a line parallel to that. It hits here. And the geometry of the whole thing is that it's going to cause that ray to pass through the focus. So we draw that. All right. In the next one, draw a line from the top of the image here through the focus. And what that will do, it will bounce and go parallel to the principal axis. It's the opposite of this. Here, the parallel line, the parallel ray to the principal axis hits here, passes through the focus. Here, if the ray passes through the focus and hits here, it's going to go back parallel to the principal axis, right? And finally, a ray passing through or emanating from here, right? The center here, going to the top there, hit there, will come right back through C. Why? Because a little bit of mathematics there, right? It's going to hit it like a tangent. You ever hear about a tangent, right? So remember, the angle of reflection and the angle of incidence is the same, but this one hits it directly straight. So you're going to hit straight, and then you're going to come back straight, right? So it's going to pass straight through the center. So when you combine these three, right? Look at this. This is that force one, right? That's force one. Look at what happens. So when we combine the three rays, and if we were to put our eye maybe here, the image that we're going to see is actually going to be real. They say real, meaning it doesn't form in the mirror, right? It forms outside here. If we were to put a screen here, if this room was darkened maybe, and let's say this red object here was a candle, and you were to put a translucent screen, you'll actually see the image here, right? When you speak of a real image, it's an image that can be formed on a screen, right? It's not an image that is inside of the mirror that you see. No, this image will appear as though it's in front of the mirror, right? And you can actually, if you, as I said, you put a screen here, you're going to see it, right? And then the opposite. Of course, if you put the object here, right? If you put the object here, notice you draw one parallel there, bounces off there, pass through the focus, right? Draw one from here through the focus, that's going to bounce back parallel. And then you draw one from here through the center, it's going to hit there at right angles and bounce straight back. So this is your image here. Notice here, if you put the object between C and F, right? If you put the object between C and F, here is where you'll see the image. If you put an object, beyond C here, the image is going to be seen here and it's going to be smaller. Notice here what? In this one, the object is smaller, the image is bigger. Here, object is larger, but the image is smaller. Right? And a good question that you could ask is, what about if I put the object closer than the focus, maybe here? What's going to happen? What's going to happen? As a matter of fact, there is I think there is a picture in the the notes we have of a concave mirror being used as a makeup mirror. Wait, let me see if I can grab that. Yeah. This is inside of our notes, right? This picture, this picture here along with the ray diagram. If the object, if you put the mirror very close to you, and in this case, this is one of the use case of a concave mirror, right? Yes, there are makeup mirrors that can be plane mirrors, right? I'm not disputing that, right? But you can also have a makeup mirror that is slightly concave. And what will happen is that the effect is that, as you see from the ray diagram there, right? You're going to see things a little bigger. And that's what you want in a makeup mirror. You want to see little details in your, a little pimple, a little something in your eyebrow or what. You want to see it bigger, right? Here is a good use case of a makeup mirror. I think sometimes there is what we call shaving mirrors as well, right? The one I have in there is a plane mirror. It's not a concave mirror. But you can have a shaving mirror too that is concave, and it's going to give you a bigger image as you get a mirror close to you and you're shaving. It's going to, and notice the image this time, it's virtual, right? It seemed to be somewhere the back there, right? In the mirror. And it's good for those cases, right? It's good for those cases. So you see them a lot in, as I said, makeup and shaving mirrors, right? Okay, so let's deal a little bit now with convex mirrors, right? So convex mirror. And give me a second again. Let me just go grab this image to show you what a convex mirror would look like. Well, yeah, so this is our image here. And we have an example here of what we call a convex mirror. But notice here, the curvature is this way and not the other way, like when we were dealing with concave mirrors, right? So the silvering on this here is okay. It's this side, but the curvature is away from your object here, right? Good. And we're actually seeing a real life application of a convex mirror here on this guy's helmet. But you see them a lot. You see them a lot on, I mean, in your vehicles, some of the side mirrors and so, right? There's be a convex mirror. Some of them are like that. As a matter of fact, there are times when that rear view mirror is not, it's not a plane mirror, right? Some cars are different, right? Some have a plane mirror, some have a convex mirror. Same thing is true with your, those side mirrors that you have. I use them a whole lot when I drive, right? Those two ears like at the side. Very often they're convex because you see a wide area and it actually brings it down to a smaller image, right? But remember, you're close, so the image, even though it's small, as you see here, right? So the object is big, right? And again, we do the ray tracing, right? So we go one straight there, right? Now it's going to bounce away that way, all right? But you can project it backwards through the focus. Notice where the focus is for the convex mirror. And we can see, remember we talked about a negative sign earlier, right? So because the focus is behind here, right? That's why you see that negative sign, right? Being there. We're going to talk about it. And same thing with the radius of curvature is this side, because the curve is this side, right? Look here. Curvature is this side. So your center of curvature is here. Your radius of curvature is here, right? And your focus is also behind here. So you draw straight there, draw through the focus. Okay, we got that one. Then this one here, all right, let's say here, and it bounces straight off, right? Parallel. So down here, you go parallel, it bounces off like that, pass through the focus, right? Then there's one that is parallel. Notice when you draw here, hit, is going to come off parallel here, right? And then one has to go through the center, right? Here. And where the three of them meet up, that's your image there. That's your image, starting from your principal axis here. What you're seeing here is that the image is a little smaller, right? But the use case scenario is that it brings all what is happening here, right? It can show a whole lot of what is happening on a smaller scale, right? As we said, all that is happening here, all that is happening, not just this object. If you have several objects here, it's going to show up behind here, right? It's going to appear behind here. It's a virtual image, but you're going to see, look, a whole lot. As you see with this guy here, right? You can see that all the people that is behind him and so, right? He's seeing, I mean, a person watching the helmet will see all of that, right? And that actually tells you the kind of uses you can use for a convex mirror, right? You can have a situation where, as we said, you can, what you call it, your rear view mirror can be convex, right? And that will make the object seem a little closer, which is good for you because you're going to start to drive now as though the vehicle is a little closer to you. So you're not going to change lanes and do anything erratic, right? That can cause problems, right? Same thing with your side view mirrors. You're able to see a lot of detail of what's happening around you, especially behind you. And you see it inside the convex mirror that makes up your side view mirrors, right? Those little areas at the side. As I said, some cars will have plain mirrors there, but some of them would actually have a slight curvature, convex mirror that will help you to see more of what's happening behind you, right? I think mine that I have outside there is a little curved because when I look in a mirror, I see almost what's going on behind my car, right? I see a lot of details, so it helps me, with. I see if there's a vehicle that is approaching me from the outside, and so, or if there's a motorbike, these guys that would ride on the inside of you, and so, and I glance there, I know what's going on. So yes, that's a very good use case of convex mirrors. And there's a little illustration of how you can construct the image inside of it. What I'll do, I'll try to, somewhere in this video, I'll insert a little video that I took off YouTube that will help you to understand how these images and so can be constructed depending on where the object is, right? And you can know, well, how do you get the image, right? Whether it's real, whether it's virtual, and so, right? I'll put in a little video in this whole setup here.
Hi friends, if you stand in front of a plane mirror, do you know exactly where your image will be formed? That's right, it's going to be behind the mirror. The distance between the image and the mirror will be exactly same as the distance between you and the mirror. We also know the properties of the image. It's going to be virtual and upright, and the image will be the same height as you. But now if I replace the plane mirror with a concave mirror, can we predict where the image will be formed? It's not so easy now. Or if I replace it with a convex mirror, where will the image be formed? What will its properties be? In this video, I'm going to make the topic of image formation for spherical mirrors, that is the concave and convex mirrors, really easy for you. And as usual, we'll finish off with our top 3 questions on this topic. Before we look at spherical mirrors, let's do a quick recap on how to draw the ray diagram for a plane mirror. As we discussed, we know all the properties of the image formed by a plane mirror. Image height equals object height, and image distance equals the object distance. So we can cheat here. We first draw the image and then we draw the light rays and produce them backwards to match the image. we take 2 rays from each point on the object, because you need a minimum of 2 rays to obtain a point on the image. So for a plane mirror, the image is drawn first and then the light rays. But we can't do this for a concave or a convex mirror because we are not sure of the properties of the image. We must use the light rays and the light ray rules for obtaining an image for spherical mirrors. Let's start with the concave mirror. The concave mirror is a converging mirror. For image formation, we need to draw the concave mirror accurately. Let me show you a simple trick for that. Draw a line representing the principal axis. Using a ruler, mark 3 points where C is at 0 cm, F is at 3 cm and P is at 6 cm. You can take any convenient distance. F should be exactly in the middle such that CF equal to FP. C is the center of curvature, F is the focus and P is the pole of the mirror. Now use your compass to draw an arc for the concave mirror. The compass point should be placed at C, the center of curvature, and the radius of the arc will be CP, which is equal to 6 centimeters in this case. Mark the back side of the mirror with these dashes. Now let's talk about the rules for image formation of a concave mirror. Light is a very visual topic, so I suggest you to keep pausing the video and drawing the ray diagrams for these rules in your notebook. Then you'll get a better feel of what is going on. There are 4 rules for a concave mirror, so let's take a look at them. Rule 1. A ray of light which is parallel to the principal axis after reflection passes through the focus. Rule 2. A ray of light passing through the center of curvature is reflected back along the same path. Do you know why? That's right. The ray of light falls normally, perpendicular to the mirror. That's why it's reflected back along the same path. Rule 3. A ray of light passing through the focus after reflection becomes parallel to the principal axis. Can you see that rule 3 is exactly opposite of rule 1? It's due to reversibility of light. Rule 4. A ray of light which is incident at the pole of a concave mirror is reflected back, making the same angle with the principal axis. It looks like a plane mirror type of diagram since the principal axis is like the normal here and the angle of incidence is equal to the angle of reflection. Let's place the 4 rules that we have learned for concave mirrors on our concept board. Remember, when drawing an image, you need 2 rays from a point on the object. So for concave mirrors, you need to select 2 rules that are convenient for the diagram. Now an important note here is, avoid using the 4th rule unless really necessary, because it's hard to measure angles accurately with your protractor. So it can lead to inaccuracies in the diagram. So basically you need to use 2 out of the first 3 rules for concave mirrors. Now I'm going to be the object and I'll go and stand in front of the concave mirror and you need to find my image. So are you ready? Let's try it out. Here I am on the principal axis. I'm far away from the concave mirror. I'm going to walk towards the mirror and stand on different places on the principal axis. And you'll see that the image will change based on my location. So let's start with case 1. I'm beyond C, the center of curvature. You need to consider the rays from the top of the object. So from my head. And remember, we need to take 2 out of the first 3 rules. So let's use rule 1. For the ray that is parallel to the principal axis, after reflection, it passes through the focus. And for the second ray, we can use rule 2. So the ray passing through the center of curvature gets reflected back along the same path. Now what does the intersection of these two reflected rays represent? That's right, it's the image, and it's the image of my head, because we started with the rays from the top of the object. Now where is the feet in my image? You don't need to draw the rays for that. The feet lie on the principal axis. So we can simply extend the image to the principal axis and find the bottom of the image. So as you can see here, using the ray diagram, we have found the position of my image. What are the properties of the image? There are 3 points here. Is the image real and inverted, or is it virtual and upright? Is the image magnified, diminished, or is it the same size as the object? And what is the position of the image? So let's see what are the properties of the image for case 1. As you can see here, the image is real and inverted. It's real because it's formed by the real intersection of light rays. And it's upside down. So it's an inverted image. As you can see, the image is diminished because it's smaller than the size of the object. And the position of the image is, it's located between the center of curvature and the focus. You'll find similar diagrams in your textbook. Of course, I won't be the object there. Usually we use an up arrow to represent the object, and it's marked as AB. And the image is also going to be an arrow and marked as A dash B dash. Here the arrow of the image is inverted since it's an inverted image. Now let me walk closer to the mirror. I'm going to stand at C, the center of curvature, for our case 2. Once again, let's draw the rays from the top of the object. We need to use 2 rules from the first 3 rules. So for our first ray, let's use rule 1. The ray that is parallel to the principal axis after reflection passes through the focus. Now I can't use rule 2 since I am standing on the center of curvature. So let's go ahead and use rule 3. The ray that is passing through the focus after reflection is parallel to the principal axis. So this is our second ray here. Where is my image? As you can see here, it's exactly below me. What is the nature or properties of the image? It's real and it's inverted. It's the same size as the object, so the same height as me, and its position is at the center of curvature. If you try drawing the ray diagram for this case 2, where the object is at the center of curvature, you might find that you're not getting the image exactly at the center of curvature. Now this can happen if the focus F is not exactly between P and C, or if the rays are not drawn very accurately. So to avoid such errors, an important exam tip is to use the cheating trick, just like we did in plane mirrors. So you first draw the inverted image at the center of curvature, and the image height is equal to the object height, and then you draw the rays. So then you'll get the image accurately. Now I'm going to move closer to the mirror. So this is our case 3, where the object is between the center of curvature and the focus. I would like you to pause the video here and find the image yourself using a ray diagram. Also write down the properties of the image formed. So what is the nature of the image you got? That's right. The correct answer is it's a real and inverted image that's magnified. So this is the ray diagram, and as you can see, the position of the image is beyond the center of curvature. Now I'll move ahead and I'm going to stand at the focus of the concave mirror. Again, let's use 2 rules out of 3. As you can see, this is an interesting case because the reflected rays are parallel. The reflected rays never meet. So our image is formed really far away at infinity. The image is real and inverted and it's highly magnified. Now let's look at the last case where I move really close to the mirror. The object, that is me, is between the pole and the focus here. Now let's use rule 1 and rule 2 to draw the light rays from the top of the object. And as you can see here, the reflected rays are divergent. So let's produce them backwards to obtain our image. Wow! Can you see? I'm magnified here. So what are the properties of the image? The image is virtual and erect. It's magnified. And as you can see, it's formed behind the mirror. Do you know how the concave mirror is used in this case? That's right, it's used as a shaving mirror. Since you appear magnified, it's much easier to shave. Now that we are done with the topic of concave mirrors, let's take a look at the other type of spherical mirrors, the convex mirrors. The convex mirror is a diverging mirror. For image formation, we need to draw the convex mirror accurately. Similar to the concave mirror, draw a line representing the principal axis. Using a ruler, mark 3 points where P is at 0 cm, F is at 3 cm and C is at 6 cm. You can take any convenient distance as long as F is exactly in the middle between P and C. So the distance CF is equal to FP. P is the pole of the mirror, F is the focus and C is the center of curvature of the mirror here. Note that in a convex mirror, the F and C are on the opposite side compared to a concave mirror. Now use your compass to draw an arc for the convex mirror. The compass point should be placed at C, the center of curvature. The radius of the arc will be Cp equal to 6 centimeters in this case. Mark the back side of the mirror with these dashed lines. Now let's talk about the rules for image formation of a convex mirror. Just like concave mirrors, there are 4 rules for a convex mirror. Rule 1. A ray of light which is parallel to the principal axis, after reflection, it appears to be coming from the focus. Can you see that the real rays are shown in solid lines and those behind the mirror are shown with a dashed line? Rule 2. A ray of light going towards the center of curvature of a convex mirror is reflected back along the same path. Rule 3. A ray of light going towards the focus after reflection becomes parallel to the principal axis. Can you see that rule 3 is exactly opposite of rule 1? It's due to reversibility of light. Rule 4. A ray of light which is incident at the pole of a convex mirror is reflected back, making the same angle with the principal axis. Here the angle of incidence is equal to the angle of reflection. Let's place the 4 rules that we have learned for convex mirrors on our concept board. Similar to concave mirrors, avoid using the 4th rule unless really necessary, because measuring angles accurately with your protractor is hard and it can lead to inaccuracies in your diagram. So basically you need to select 2 out of the first 3 rules for convex mirrors. Once again, I'm going to be the object and I'll go and stand in front of the convex mirror and you need to find my image. So are you ready? Let's go ahead and try it out. Here I am on the principal axis at a certain distance from the convex mirror. Again, we need to take the light rays from the top of the object. So my head. Remember, we need to use 2 rules from the first 3 rules. So for the first ray, let's use rule 1. The light ray that is parallel to the principal axis after reflection appears to be coming from the focus. And for the second ray, let's use rule 2. The light ray which is going towards the center of curvature gets reflected back along the same path. Now where do these 2 reflected rays meet? The reflected rays are divergent here, so we need to produce them backwards. And the point where they meet is the position of the image of my head, since we considered the rays from the top of the object. Now where are the feet in my image? That's right, on the principal axis. So we simply need to extend the image down to the principal axis and we get the bottom of the image. So you don't need to draw rays for that. And as you can see from this ray diagram, we have found the position of my image. What are the properties of the image formed here? The image is virtual and upright. It's virtual because it's formed by the reflected rays extended backwards. The image is diminished, and as you can see, it's formed behind the mirror. Now let me walk closer to the convex mirror. Again, we are going to use 2 out of the 3 rules to obtain our image. And as you can see, the image formed has similar properties. It's virtual and erect, it's diminished, and it's formed behind the mirror. Remember, the concave mirror had so many different cases, but the convex mirror is the easy one in the syllabus because it doesn't matter where you stand in front of the mirror, the image properties are always going to be the same. It's going to be virtual and erect, diminished, and the image will be formed behind the mirror. Have you noticed the convex mirrors used at the intersection of roads? What is the nature of the image produced in the convex mirror? That's right, it's always virtual, upright, and diminished. Imagine if that convex mirror gave an inverted image, then the driver would get all confused and an accident may happen. So the convex mirror always produces a virtual, upright, and diminished image. I hope the image formation for concave and convex mirrors is super clear to you now. Light is a very visual chapter, so I would suggest you to practice by drawing ray diagrams and trying to predict where the image is formed. Then you'll feel more confident about these light ray rules.
Right? Just a little bit of mathematics. I'm not going to delve into anything more. In that you can actually do some calculations involving magnification and where the object is and where the image is in any kind of mirror, right? There are equations that govern these things. So let's do that, right? I think yeah. Let's deal with the mirror equation. Now let's talk a little about yeah. Let's talk a little about mirror equation. Oh my, I think the mirror equation, right? Mirror equation. So basically, this is the mirror equation. 1 over d naught plus 1 over d1 is equals to 1 over f, right? And you can figure out what d naught is. It's not d naught, it's the O, right? D subscript O, it's the object distance right? This here is the eye, right? It's the image distance. Image distance. Um, um, that there is the focal length, right? So that's your mirror equation, plain and simple. I'm not sure if you can handle in mathematics of if you're given f and d1, if you can find d0. I'm not sure about that. And then there's what we call a magnification equation, right? Magnification is equals to the image height over the object height, right? How big are the images compared to the height, right? Yeah. And we're going to go with okay, minus d I over do, right? And there is a reason for this minus sign business here, right? There is a reason for this minus sign. I just want to capture all the meaning of these minus signs and so that's what I want to capture. Let me see if I can cut it straight from the notes somewhere. Yes, let me move this to the side and just get the one second. No. All right, so that there, and trying to see if I can put all in one. Yeah. All right, let's put that here. Yeah. All right. So this is explaining all the signs, right? So if you're dealing with a concave mirror, F is positive, right? If you're dealing with a convex mirror, F is negative. And there's a reason for that, right? In a concave mirror, the focal point and the focal length and so is over in the real side of the mirror, right? Remember, if you have something like this, right? If it's curved like this, down here is where your F might be, right? And that this is where you and I are seeing, right? But with the convex mirror, that's when it's turned the other way. Let me just if you're dealing with a convex mirror, right? And okay, down here's the silvering. The focal point is here, right? It's on the side of the mirror. Well, this is the real side, right? This is the virtual side of the mirror, right? So that's why we're using a negative for anything that is virtual, right? Yes, and that's what I go on to see here. D naught is positive if the object is in front of the mirror. In other words, you have a real object. D naught is negative if the object is behind the mirror. It's a virtual object, right? Yeah. Right. Well, usually you don't have a virtual object. You have a virtual image, right? Yes. And the image distance is positive if the image is real and it's in front of the mirror. D subscript I is negative if the image is behind the mirror, right? The magnification is positive for an image that is upright with respect to the object. M is negative for an image that is inverted with respect to the image, right? So the negative doesn't mean that the object is actually diminished, right? It simply means it's inverted, right? If the magnification is greater than 1, well, you know the thing gets bigger. If it's less than 1, you know it gets smaller. But the sign, positive or negative, tell you whether the thing is upright or inverted. Just keep this in mind as you look at some examples, right? So I'll take the example or two that we find inside our notes, right? Maybe we can take a concave mirror for us, right? I think they have a couple of examples here, right? Let me see if I can cover all of them. So this is an example that comes from our notes, right? Yeah, right. This is one from our notes. So you're dealing with a concave mirror here. They give you some bits of information. You have a 2 cm high object placed 7.1 cm from a concave mirror they give you the radius of curvature. They want you to find the location of the image and its size, right? And by the way, this kind of problem can be solved by drawing as well, right? Using the same method I showed you about drawing everything to scale and all of that, right? But you can also calculate it. I'm not sure if everybody can handle the mathematics, right? Good. So we got what? You can get the object is this away. They give you the radius of curvature as this, so we can get from that the focal length, which is half of it. What do they want? They want you to find the location of the image and its size. All right. So remember the formula. Let me go back to the formula. 1 over d I plus 1 over d naught equal 1 over f, right? Remember that? Right? So they're using that formula. So they rearrange it back. And remember, they want the location of the image, right? So they're finding d subscript I. So we want to find 1 over d subscript I first. And then we'll flip it around, right? Good. So that will be equal to 1 over f minus 1 over d subscript 0, right? So 1 over f, I think f is what? F is 5.1 naught. That's half of this 10 cm, right? 10.2. Remember, the radius of curvature is twice the focal length, right? So you have to divide it by 2. And that's what we did here, right? We divide by 2, we get 5.1. Minus 1 over 710. They actually give you how far away is the object. And you have to do a little bit of mathematics there. I'm not sure if you know how to do the math, right? Your fractions and so on. You get this, right? But remember, 1 over d equal to 0.055, right? So to get, d subscript I, to get this, you have to flip it over. Take 1 over 0.055, and that's going to give you 18, right? And so that's the location of the image. And the fact that it's 18 cm, right? It's telling you that the image is, what did notes say? Real one. Let me go back to the image distance is positive. The image distance is positive. The image is in front of the mirror. It's a real image, yes. Right? Good. And next, now we have to calculate the magnification they want. No, they want the image size. What's the size of the image, right? Good. So did we cover this formula? The magnification is given by minus di over do, right? Good. So di, oh, did we get that? Let me see if I gave you that formula as the magnification. Where is the magnification? This image height over the object height. Oh, what we probably didn't do here, we're supposed to say m equal r down here, h I over ho, right? I guess that's missing it. The I over, right? So yes. So I guess I should have written this way. So we're making use of this formula here, right? Because I think we got, we get di and do, right? Which will now give us what is needed here, right? Let's see what's going on. Yeah, let's see what's yeah. So hi is equals to minus. I wonder whether you. Yeah, so let's use the formula. di over do minus of it is equals to hi over ho, right? So I think we know what I want. Find location of the image, its size, right? So the height of the image, this one you want to find. So hi is going to be equal to minus di do times ho, right? So the distance of the image, I think we just found it to be 18. So you get minus 18 over. The distance of the object was some 7.1 cm times ho. The thing was 2 cm, right? So you work out this and you get an answer of, so that's what they have here, right? Minus 5.1. And how are we to interpret that? Right? It says that the negative value for h subscript I indicates that the image is inverted with respect to the object. That's all that it means, right? So it is somewhat magnified, got a bit bigger. The object originally was 2 cm, now it's 5 cm, right? 5.1. And in the negative sign, just telling you that you see an upside down image, right? So yeah, it's a bit of mathematics. I'm not certain whether you were able to follow the mathematics, right? Yeah, I'm not certain. And I think all the others, um, they have some others in the notes. You can always cover them. There's one by a concave mirror, and then there's one by that is a image form, virtual image by a convex mirror. So this one, yeah. This one is a convex mirror, concave mirror. Second one. And the last one is a virtual image formed by a convex mirror. All right, I'm not sure if you can handle this mathematics. Mm, Or maybe we can, let me just look at them and see what's going on. So, oh, I think in this one, they actually, you have a concave mirror still. In the first example, the image was real. In this case, they say the image is virtual, right? Um, and that should tell you that what's happening here is that the object is placed very close to the mirror, right? So what happens is that there's an enlarged, remember that story with like a shaving mirror or one of those makeup mirrors? Yeah, that's what's happening here. So you place something in front, 6 cm in front of a concave mirror. Notice the focal length is 10. So we get it very close to the mirror, between the focal length and the mirror itself, right? Determine the location of the image. And they say the object is 1.2 cm high. Find the image height, right? And well, here's our formula again. So we want the location of the image, that's D subscript I. Same calculations, right? And you flip this over and you get minus 15 cm, right? So what this negative sign is telling you is that the image is not a real one. It's in the mirror. It's like one of those, as we said, the shaving mirror or the makeup mirror, right? And then we use the magnification formula now. And indeed, you see there's a magnification, right? The object was actually 1.2 cm. Here it's 3 cm, right? So there's no inversion of the image, but the image got bigger, right? Maybe the next time we talk, maybe you can talk about whether you can handle this kind of mathematics, right? Whether you know your fractions and so to that extent. All right, maybe we'll take a last one, and I think this one has to be a convex mirror, right? Yeah, second, let me cut it. Yeah, so we go in convex, right? Yeah. So here, convex mirror is used to reflect light from an object 66 cm in front of the mirror. The focal length of the mirror is, notice they use a minus value, right? Because we said that the negative side or the virtual side, right, is where the focal point is going to be for a convex mirror. And that's why you use a negative 46, right? And then they say find the location of the image, the magnification. So again, we're using the same formula, right? I know I did give you the formula in this form, that 1 over D subscript I plus 1 over D subscript O equal to 1 over F, right? But it seems as though in these problems, they always want to find this. So they bring that over here, right? And that's what they're using there. So we got all the numbers there. And then you flip this over and you get negative, right? And the negative sign is telling you that the image is behind the mirror. It's a virtual image, right? That's your image there. And you use the magnification equation, right? And the magnification, according to this here, is 0.41. It means that the image is a little smaller than the object, right? And the simple reason is because, okay, if something is in front here, and when it goes behind here, right, it might get a little smaller, right? That happens. Yeah. So you must give me a feedback as to whether how you feel about the mathematics and whether it's something too heavy for you. I will make a decision what to do. right? I'll insert into this presentation a couple of videos that would illustrate certain things, right? To help you, um, visualize certain things, to be able to draw certain ray diagrams and so on. Good. So we took care there of, as we said, reflection in plane mirrors, in um, concave mirrors, and in convex mirrors.